Hello everyone, I am Srishti Shreya from EC Section A and today I am here to discuss about the topic Integrator and Differentiator. Integrator and Differentiator are some of the applications of operational amplifiers. First we will discuss about integrators. Integrators can be understood as it simulates mathematical integration. They are used in analog computers and wave shaping networks. In integrator, we can say that the output voltage is the integration of the input voltage. Integrators are of two types, ideal integrator and practical integrators. The circuit shown here is of an ideal integrator and we can see that the inverting input terminal of the op amp is connected to a resistor which is given an input voltage, and there is a capacitor which has its one end connected to the resistor and its other end going to the output voltage. For deriving the relation between the V output and V input, we will use the nodal equation. We can use the nodal equation for finding the rate of change of output voltage in terms of input voltage. This can be given as 0 minus V input by R plus C into differentiation of 0 minus V output with respect to time will be equal to 0. Now we can say that minus V input by R plus C times minus of V output, differentiation of minus of V output by dt is equal to 0, or we can say that minus V input by R is equal to C times differentiation of V output with respect to dt. This can be further simplified as differentiation of V output is equal to minus V input divided by R into C. This differentiation of V output is done with respect to time here. Integrating we can say this as differentiation of V output is equal to minus V input by RC into T. Integrating both sides, integrating both sides, we get integration dV naught is equal to minus V in by RC integration dt. This implies that V naught is equal to minus 1 by RC integration V input dt. This is the final equation which gives us the relation between the V output and V input, and we can see that the output voltage is expressed in terms of the integration of the input voltage. Now we will discuss about the practical integrator. Now in ideal integrator, it uses a capacitor in the feedback path which is open to DC. This implies that the gain at DC is the open loop gain of the op amp. But in a practical integrator, we can say that any DC error voltage due to offset error will cause the output to produce a ramp that moves toward either positive or negative saturation. So in practical integrator, we use a feedback resistor also in parallel with the capacitor. Practical integrators must have some way of overcoming the effect of offset and bias current. The best solution is to connect a feedback resistor in parallel with the capacitor such that this feedback resistor is greater with respect to the R input, so that there is the negligible effect on the output waveform. Now coming to the next part of this video, which is the differentiator. Differentiator can be understood mathematically as mathematical differentiation. They are commonly used in wave shaping circuits to high frequency signal component in input signal. The op amp based differentiator produces an output which is equal to the differentiation of the input voltage. The circuit shown below is the circuit of an ideal differentiator. Here we can clearly see that the inverting terminal of the op amp is connected to a capacitor which is given a input voltage, and there is a resistance which has one of its end connected to the capacitor and the other end is connected to give the V output. The positive terminal of the positive or the non-inverting terminal of the operational amplifier is grounded, and from the virtual short concept we know that the voltage at the non-inverting terminal is equal to the voltage at the inverting terminal. Therefore, since here it is grounded and the voltage is zero, therefore the voltage at inverting terminal of the op amp will also be 0. For finding the relation between V input and V output, we will use the nodal equation at this point. By using the nodal equation at this point, we can say that C times differentiation of 0 minus V input with respect to dt plus 0 minus V output by R is equal to 0. This implies that minus C differentiation of V output by dt is equal to V naught by R, or we can say that V naught is equal to minus RC differentiation of V input by dt. This relation here is giving us the relation between the V output and the V input, and we can clearly see that the V output is uh, depicted in terms of the differentiation of the V input. That's why this circuit is known as the differentiator circuit. Now the differentiators are also of two types. One is the ideal differentiator that we have discussed earlier, and the second is this practical differentiator. Practical differentiator uses a feedback resistor also. Feedback uses a feedback resistor here and one resistor in series with the capacitor. This is done because the capacitor has very low impedance at high frequencies. The combination of RF and C form a very high gain amplifier at high frequencies. This means that a differentiator circuit tends to be noisy because electrical noise may consist of high frequencies. The solution of this can is that connection of a resistor in series with the capacitor. This resistor R in should be very smaller in comparison to the feedback resistor to have negligible effect on the desired signal. In the next part of this video, we will discuss about the output waveforms that are formed when different types of waves are given in integrator and differentiator circuits. For the first, we will have a square wave in integrator circuits. Since it is square wave, its output waveform will be like a triangular wave of this type, and for a differentiator circuit a square wave will have an output waveform something like this, at like the spikes, because it has been differentiated. Something like this will be the output waveform for a square wave in differentiator. Now the second wave that we take as input is the sine wave. For sine wave, we know that in integrator circuit the sine wave will be converted to uh, a negative of cos wave, because we know that integration of sine is equal to negative of cos. Therefore now we will have to draw the negative of cos, which will be like this. Therefore, this is the output waveform when a sine wave is given in an integrator circuit. For differentiator circuit, when a sine wave is given, we can have the output waveform as cos wave, because we know that differentiation of sine x is given as cos x. So this is how this circuit output waveform of a sine wave will look like in a differentiator circuit. To end my video, and pay my highest and biggest gratitude to my professors for imparting me with all this knowledge. Thank you.